Hello everyone, I welcome you all to the next week of the course on automation in manufacturing. The lecture 1 of week 8, that is mechanisms, is on application of indexing mechanisms in automation. So in this lecture we will be studying various indexing mechanisms, and then we will have a discussion on application of these indexing mechanisms. So let us look at the outline of the lecture. At start we will see the meaning of indexing mechanism. There are various types of indexing mechanisms are used in the industry. These are ratchet and pawl mechanism, rack and pinion mechanism, Geneva mechanism, cam drive mechanism. We will see the construction details of all these mechanisms and where we can apply these mechanisms to get the required automation done. In industry and in shop floor, we need to have a series of step movements for variety of purposes. Say it may be for processing of the work part at various locations, at various stations, or it is indexing or selection of a specified or a desired cutting tool from a bunch of cutting tools. To carry out such operations, to carry out the stepwise operations, indexing mechanisms are helping a lot in the automation process. Indexing mechanism in general are converting the rotary motion or oscillatory motion into a series of steps, and that stepwise motion is utilized for our intended purpose. It may be for the processing or it may be for the tool change. Very important simple application of indexing mechanism is in the tool turret. Basically, tool turret is nothing but a mechanism in which we are storing the cutting tools on a production lathe machine. In our previous classes, we have seen the concept of the lathe machine or the CNC turning machine. In lathe machine or CNC turning machine, we need to utilize a number of tools to carry out the operations. But to select a proper tool and to get the proper tool, we need to have certain mechanism. That mechanism must be productive, it must fast, it must be very accurate. So for that purpose, we need the indexing mechanism. To understand the concept of tool turret, let us look at the diagram which is there on your screen. The tool turrets are basically used in turning operations. In turning operation, we are reducing the size of axisymmetric work parts. We are working on axisymmetric work parts. Consider a cylindrical bar is held in a chuck. Chuck is a work holding device. The chuck is driven by an electric motor. As the spindle rotates, the chuck is also rotating. As the chuck is rotating, the work part will also rotate about its own axis. We are using a cutting tool which is harder than the work part, and by having the relative motion of the cutting tool with the work part, we are reducing the size of the work part. But during the turning operations, we may need to have multiple number of cutting tools. So instead of changing them manually, can we have an automatic option? Can we change the tool automatically? So that will save our lot of time and we can enhance the productivity. So for this purpose, we are using a hexagonal turret. The shape of the equipment is hexagonal, that's why it is called as hexagonal turret. Turret on the faces of the turret, we are mounting various cutting tools. So on your screen you can see this is the hexagonal turret. This is a plan view, the elevation in this. So we are rotating the hexagonal turret about its this axis, this vertical axis, but this rotation is not continuous, it is in incremental. And to have that incremental rotary motion of the turret, we need to have certain indexing mechanism. So as per the need, we are rotating the turret. The tool will come in contact with the work part by having the longitudinal movement of the cutting tool with respect to the work part, and then we are getting the required operation done, that is reduction in the diameter. Thus, we can say that in production machines, we need to have an indexing mechanism for processing of the product at various stations. At these stations, the product need to be stopped for the required operation. In addition to this stepwise motion, we also need to have the indexing mechanism for feeding of the machine tools. In general, 5 basic types of indexing mechanisms are used in the industry, and these are ratchet and pawl mechanism, rack and pinion mechanism, Geneva mechanism, and cam drive. So let us see these 5 different types of mechanisms one by one. The first mechanism is ratchet and pawl mechanism. This device allows the linear or rotary motion in only one direction. This mechanism has a wheel that we call a ratchet wheel. On the periphery of the wheel, there are teeth. These teeth are engaged with a driving pawl which is pivoted in an arm. The arm is connected to the center point of the spindle. We can swivel the arm, and by swiveling the arm, the driving pawl is driving the ratchet wheel. So let us consider the driving pawl is moving in the anti-clockwise direction. As we are moving from right to left in anti-clockwise direction, the pawl is driving the ratchet wheel. It will move the ratchet wheel in anti-clockwise direction for certain angular distance. Afterwards, the pawl will return due to the spring force which is applied on it. Again, we have to drive the arm, we have to rotate the arm into in anti-clockwise direction. So as we rotate it once again, we can have another incremental angular motion in the ratchet wheel. To restrict the opposite direction motion, that is the clockwise direction motion, we are using a locking pawl. Locking pawl arrangement can be seen on your screen. It is spring loaded locking pawl. But the springs are used to have the continuous engagement of the pawl with the teeth of the ratchet wheel. So as the driving pawl is driving, the wheel is rotating in anti-clockwise direction. To avoid the rotation of the wheel in clockwise direction, the locking pawl is used. Generally, the rotary machines which are operated by air, by pneumatics, such arrangements are used. The teeth or the pawl are at an angle so that when the teeth are moving in one direction, the pawl slides in between the teeth. As I mentioned, there is a spring, and that spring is forcing the pawl back into the depression between the next teeth. So in this way, the springs are ensuring the continuous contact of the pawl with the ratchet wheel. The advantage of ratchet and pawl is that they are not mechanically interlocked. We can easily remove them. Therefore, the ratchet and pawl mechanism is easy to set up. But if the table is heavy, if the inertia of the table is very high, during that incremental motion of the table may override. It may overrun due to its own inertia. So as we are giving angular motion, the locking pawl will not have the sufficient strength to avoid its reverse motion. That may be due to the heavy table. As there are no mechanical interlocking of its elements, the maintenance of the system is quite easy. The important applications of the ratchet and pawl mechanism are in jacks and the winding mechanisms, winding machines. Jacks we are using to lift the systems, to lift the products, and winding machines are used to wind the wire or the cables either manually or automatically. In machine tools, we are using the ratchet and pawl mechanism, rotary indexing motion to the tool turret. So in this way, we can feed the workpiece to the required tool. We are changing the tool according to our need, and then we are getting the required work done. Well, the next mechanism is rack and pinion mechanism. In general, the rack and pinion arrangement is used to convert the rotary motion of pinion into the linear motion of the rack. Pinion is an element which is rotating about its axis. So that rotary motion of the pinion, generally the pinions are driven by electric motor. And as we are rotating the pinion, it is converting that rotary motion into the linear motion of the rack. The rack is again a mechanism, a mechanical element which is having teeth, and we can consider the rack as a small portion of an internal gear with infinite radius. We will see the diagram of the rack in the next slide. But in indexing application, we need the reverse case. So what is the reverse case? The reverse case is we need to get the rotary motion of the pinion due to the linear motion of the rack. We are providing linear motion, linear reciprocating motion of the rack, or we can have the straight one direction linear motion to the rack, and that should be converted into the rotary motion of the pinion, and we are attaching the work part, we are attaching the work table to the pinion. So as the pinion is rotating incrementally, we are getting the indexing of the table which is connected to the pinion. So in this way, we are getting the indexing of the table which is attached to the pinion by the linear motion of the rack. To have the indexing mechanism using rack and pinion, we are using a piston to drive the rack, which causes the pinion gear engaged with the rack, and the rack will drive the pinion gear. To have the contact of the rack and pinion, we are using clutch. These type of arrangements are not suitable for high speed operations. since they are mechanically interlocking with each other, when we want to have very high speed indexing, so for that purpose these kind of arrangements may not be suitable. So let us look at the schematic, or let us look at the arrangement. Right, so on your screen you can see there is a rack. So rack is a device which are having teeth, and there is a pinion. Pinion is nothing but a gear. This gear is having external teeth. The rack you can consider a part of an internal gear of infinite radius, and that internal gear, as we know well, it is having internal teeth. The internal teeth of rack are engaged with the external teeth of the pinion. If I push the rack in linear direction, it will drive the pinion, and that is our intended motion of the pinion. So in this arrangement, we are also using an adjustable stop which will control the linear motion of the rack. This piston cylinder arrangement is working based upon either hydraulic energy or the pneumatic energy. We will be learning about the hydraulics and pneumatics in coming weeks. As the piston is extending, as the piston is getting out from the cylinder, the rack will be pushed from left to right direction, and that will drive the pinion in clockwise direction. The rack will move along this direction. There would be incremental angular motion of the pinion. Then the rack will be disengaged by using a clutch. It will be get back to its original position, and again it will be driven by the piston. So to have the disengagement of the rack from the pinion and further engagement of the rack with the pinion, we need to have a clutch arrangement. The next important mechanism is Geneva mechanism. This is very widely used in indexing operations in the industry. This mechanism is also called as Maltese cross mechanism. Till now we have seen that the linear motion of the rack is converted into intermittent rotary motion. So in Geneva mechanism, we are converting the continuous rotation into intermittent rotary motion. We are having the electric motors, and that electrical motors are giving us continuous rotary mechanical energy, continuous rotation of the shaft. Now we need to have a mechanism which will convert this continuous rotation into the intermittent motion. So for that purpose, we are using a simple arrangement, and that can be seen on your screen. It has a wheel that we call the Geneva wheel. On your screen, you can see a Geneva wheel which is designed to provide four intermittent motions, four intermittent rotary motions of the spindle. The Geneva wheel is mounted on the spindle, and on the same spindle there is table will be mounted. So this particular view is the plan of the arrangement. There will be a table which is mounting over here. The Geneva wheel has a peculiar shape. This peculiar shape you can see over here, these curves are designed so that there would be a proper locking of the Geneva wheel with the driver wheel. The Geneva wheel also has slots, and these are slots which are getting engaged with the pin of the driver wheel. In Geneva mechanism, we are having a driver, we are having a driving wheel, and that driving wheel is mounted on the shaft of the electric motor. The driving wheel is continuously rotating. It has a raised circular block, and that raised circular block is getting engaged with the peculiar shape of the Geneva wheel. Now the operation is very interesting. As you can see on the screen, when we are rotating the driving wheel, the pin is getting engaged in the slot of the driven wheel, that is the Geneva wheel. As we are continuously rotating the driving wheel, the pin will slide along the slot and it will give the intermittent rotary motion to the Geneva wheel. On your screen, you can understand the mechanism by looking at this animation. This is the driving wheel and it is connected to the electrical motor. And as the pin is getting engaged in the slot, the driving wheel is driving the Geneva wheel, that is a driven wheel. As the pin is getting engaged and disengaged, we are getting the required intermittent motion. Basically, there are three types of Geneva motion mechanisms are used. These are external Geneva mechanism, internal Geneva mechanism, and the spherical Geneva mechanism. Spherical Geneva mechanism is not that widely used. In the simplest form, as we have seen, we can have a disc. The disc is cut into a peculiar shape with certain slots, and that will be engaged with another disc with raised surface with a pin arrangement. The number of steps will decide the angle basically. If suppose you want to have the 4 steps, naturally the angle of rotation would be around 90 degrees. The incremental rotation would be of 90 degrees. That is for the full rotation of the driving wheel. Well, on your screen you can see the arrangement of spherical Geneva mechanism. It is very interesting. So this Geneva mechanism is cut, it designed on a spherical work part. The engagement of the Geneva mechanism with the driving wheel is due to these surfaces. So these are the surfaces which are cut. These are analogous to the surfaces which we have seen in our previous slide, which are in contact with the raised portion of the driving wheel. These are the slots in which the pin of the driving wheel will get inserted, and that is driving the Geneva wheel. So instead of having a wheel, we are having a spherical arrangement which is working as the wheel itself. An important advantage of the spherical Geneva mechanism is that we can have an orthogonal transmission of the power. Here you notice that the driving wheel axis is 90 degrees to the driven wheel axis. In the previous cases, in the previous slide, we have seen that the driving wheel and the driven wheel axis are parallel to each other. So in this case, in spherical Geneva mechanism, the driving wheel axis and the driven wheel axis are mutually perpendicular to each other. They are orthogonal to each other. So this is the arrangement of the driving wheel. So it is having the shape which is cut, which is in contact with the shape of the Geneva mechanism. This is the raised portion analogous to the previous slide. This pin will get engaged with the slot of the Geneva mechanism and it is driving it. So we are giving continuous motion, continuous rotary motion to the driving wheel, and that continuous rotary motion will be transmitted into the intermittent rotary motion of the Geneva mechanism. So here we can attach the indexing table, or we can have an raised portion on which we can attach the indexing table, and we can get the required indexing done. In internal Geneva drive, instead of having the slots, or instead of having the peculiar shape which is cut on the outside of the disk, on the external side of the disk, we are having that slots or engagement of the pin in the slots in the internal side of the drive. So for that purpose we are using a disk, and in the disk the slots are cut as you can see on the screen. This disk is mounted on a shaft which is supported at only one side. So there is a cam arrangement. That cam arrangement is connected to the continuous rotary motion provider, that is a motor. We are rotating the cam, and as the cam is rotating, it is driving the driven member, that is the Geneva mechanism, Geneva wheel. The driving would be carried out by the contact of the pin in the slot. As we are rotating this cam, consider this cam is rotating, the pin will come into contact with the slot, and as the cam is rotating, it is driving the driven member. And to have the continuous contact, the outer portion of the cam would be in contact with the internal portion of the driven member, which is cut in a peculiar way. In external Geneva drive, the angle by which the drive wheel has to rotate to effect one step rotation of the driven wheel is smaller than 180 degrees. So what I'm saying here, the angle by which the drive wheel has to rotate to effect one step rotation of the driven wheel is smaller than 180 degrees, but in internal drive it is greater than 180 degrees. To have one step rotation of the Geneva mechanism, how much the cam is rotating, or how much the driving wheel is rotating in a simple Geneva mechanism. So if the arrangement is external, then the drive wheel is rotating less than 180 degrees. Then and then only we are getting one step. But in internal drive, the drive wheel has to rotate more than 180 degrees. This is the external Geneva mechanism, and you just look at here, it is getting included from this point to this point. The angle of engagement and disengagement of the pin with respect to the Geneva wheel is less than 180 degrees. So this angle, this particular angle is less than 180 degrees. The same would be, we can see here, in this case there are 4 slots. The angle of engagement from this, the angle of engagement of the pin at this point, and the angle of disengagement of the pin at this point, this particular angle is always less than 180 degrees. So that is not true in the internal Geneva mechanism. This particular angle would be more than 180 degrees. Now here you can see the engagement has been done, and the disc has to rotate more than 180 degrees to have the disengagement of the pin from the slot. The two, here you notice The pin is engaged here and it is getting disengaged at this particular point. So engagement up to the disengagement, that particular angle is more than 180 degrees. So this should be noted. Well, to have the linear intermittent motion, in previous slide we have seen that the Geneva mechanism can be utilized to have rotary intermittent motion. We can also have the linear intermittent motion using the Geneva mechanism, and that is another important aspect in automation industry. For example, you are working on a transfer line, you have to carry out multiple processing operations on the product which is moving over a platform which is intermittently moving in a linear direction. To have such movement, we are using the Geneva mechanism as well, and that particular arrangement is shown on your screen. So it has a slider. On the slider we are putting the work parts, or the slider we are having the table. On the downward direction of the on the bottom side of the slider we are having slotted plates which are attached to the slider. That slotted plates are engaged with a crank, and the crank is mounted on crankshaft. On one side of the crank we are having a pin which is in connection with the slots. We are giving continuous motion, continuous rotary motion to the crank, and as the crank is rotating, the pin will get engaged to the slot and it will drive the slider. Of course, the slider has to be supported and we should avoid its movement along the vertical direction. So proper support has to be provided. So these type of arrangements are basically used for packaging, for assembly, for stamping, for embossing, which are used in the manufacturing automation. The third mechanism is the CAMS mechanism itself. This is very interesting, but it is very complicated mechanism to manufacture. On your screen, you can see a table, and on the table, various stations are there on which you have to carry out the processing operation. This is the plan of the table. On the periphery of the table, we are attaching rollers, and these rollers are engaged to a cam. We have seen the cam mechanism in our previous week. So you notice here the axis of the table is perpendicular to the plane of paper. So here this axis is perpendicular. The axis of the cam is orthogonal to the axis of the table, but they are not intersecting. They are parallel. They are orthogonal, but they are parallel to each other. This is a cylindrical cam, and on the cylindrical cam, a peculiar shape is machined. The shape is machined in a such a way that as we are rotating the cam, there would be displacement, angular displacement of the taper. So if I rotate the cam in clockwise direction, so what will happen? When I'm rotating the cam in clockwise direction, this portion will come in contact with this particular roller. As I'm rotating in a clockwise direction, this portion would get, this portion is having the raised height. So as this portion is getting in contact with the roller, this roller will be pushed in anti-clockwise direction. So rotary motion of the cam would be converted into intermittent anti-clockwise motion of this particular table, which is mounted on a shaft. So in this way, we can achieve the rotary indexing of the table by using the CAMS mechanism. The CAM mechanism or the CAMS based mechanism is widely used in the industry despite the fact that it is very costly. Why it is costly? Because of the arrangement, because of the complexity in manufacturing of the CAM, its assembly with the table, because we need to have the precision rollers as well here. The advantage of CAM mechanism is that we can have a variety of velocities and the dwell characteristics. Dwell means the time for which we are having the stopping of, or the time during which there would not be any rotary motion of the spindle, there will not be any rotary motion of the table. And we are using the roller followers. These are the roller followers which are having the unidirectional rotary motion. We can use the indexing mechanism for processing of the work parts at various workstations. In addition to this processing at various workstations, we can have the assembly operation, automatic assembly operation by using the indexing mechanism. Consider there are two subassemblies and we need to assemble them together. So for that purpose, we can have a table, and the table has to be intermittently moved in a linear direction. So this is the assembling machine, and this assembling machine is assembling the assembly subassembly 2 with the subassembly 1. So we have to design by using the CAM operated arrangement which we have seen in our previous slide. The parts to be assembled have to be moved over the assembling machine tool. So this is the tool through over which we are moving the parts. Once the assembly is done, the table is indexed to get the next part in the line with the assembly. We can use the indexing mechanism for the inspection operation as well. A typical arrangement can be seen on your screen. There is a circular table. The table is mounted on a spindle, and the spindle is being driven by an indexing cam. Various work parts are held on the table by using various holding mechanisms, either maybe mechanical holding mechanism or magnetic holding mechanisms. The inspection may be of the geometry of the work part or the surface quality of the work part, or it may be the mechanical testing of the work part as well. So by having the intermittent rotary motion, we can carry out the 100% inspection of the work parts. The intermittent stoppage of the work part at the particular location for the inspection is totally dependent upon the velocity of the indexing wheel. Well, my friends, let me summarize the lecture 1 of week 8. In this lecture, we have studied the importance of indexing mechanisms, and then we learnt various indexing mechanisms such as ratchet and pawl mechanism, rack and pinion mechanism, Geneva mechanism, and cam drive mechanism. We have seen the principle of operation of these mechanisms. We have studied the applications of these mechanisms. In the next lecture of week 8, we will study a very useful utility, that is tool magazines of a CNC machining center. CNC machine tools are an integrated part of automated manufacturing system, and the tool change or tool related factors are very crucial in deciding the productivity of the CNC based automated system. So automatic tool changing is contributing a lot to enhance the productivity of a CNC machine tool. That's why it is essential for us to study the tool magazines. There are various types of tool magazines are used. These are disc type, chain type, and rack type. we will see the construction of these tool magazines, and at the end we will see how to change the tool automatically in CNC machine tools. Thank you very much.